notation. Okay, when we were working with derivatives, okay, let's say, let's just use f of x. If we were deriving to get the first derivative, what was the actual notation? F prime of x. Okay, the derivative or the first derivative would be f double prime of x. Okay, when we're working in the opposite direction or the inverse direction, when you're integrating, okay, we know that when you take the second derivative and you integrate, you get the first derivative. When you take the first derivative and integrate, you get the original function. Okay, but when you take just a function and integrate it, you actually get the same function with a capital letter. Okay, when you integrate f of x, you get capital F of x. Okay, that's not a notation that we've necessarily seen. Okay, now we are still working with accumulating areas. So you're still working with a summation. Okay, and this represents the height. Remember, f of x of 1 was always the height. And what was delta x? Always the what? Width. Okay, we were adding height times width, height times width. The same thing is true now, but we've got this definite integral. The difference with your integral sign, you're going to have this constant, a, which is called the lower limit. And you'll have an upper limit, which is another constant called b. Okay, so you actually have numbers in there. On homework 8, I told you to skip that part, okay, where you're finding the exact answer, okay, but you had that notation with a lower limit and an upper limit. Okay, we're still working with accumulating area. Okay, so here's the beauty of the fundamental theorem of calculus. When you have a definite integral, okay, instead of just no numbers there, it is always equal to capital F of b minus capital F of a. So we're going to actually integrate the function. We'll plug in the top limit and then subtract the result of plugging in the bottom limit. Okay, the solution to a definite integral is a number. Okay, you get a numerical answer because it represents the area under the curve. What did we say area under the curve is? It's the area between what? We've used that terminology. Between the actual function and the x-axis. Okay, we've only worked with positive numbers because all of our functions have been above the x-axis. If your actual function is below, you're going to get a negative number. But you're talking about accumulating the area. Okay, so we're going to actually use that. It really is pretty simple, and you're going to get the exact answer. Okay, so in this case, we're going to use the function f of x equals x squared plus 1, and the interval is from 0 to 3. Okay, so let's turn that notation into what's called a definite integral. So that means that we're going to integrate from 0, that's your lower limit, to 3. The function that we're integrating in this case is x squared plus 1. Okay, so instead of giving interval notation, you have a lower limit of 0 and an upper limit of 3. Now, we have to integrate the function. You don't have a plus c anymore. We're going to plug in the upper bound into the integral, and then from that value, we're going to subtract the result you get from plugging in the other bound, the lower bound. Okay, so let's integrate first. What is the integral of x squared?
1/3 x cubed.
1/3 x cubed. You want to write that over x to the third plus over 3, or 1/3 in front of it. Okay, plus what's the integral of 1? X. Okay, now we don't have a plus c anymore. Okay, we don't have a plus c. We have a definite interval. We have a numerical answer. Okay, but you have a notation way that you have to indicate the upper and the lower bound. You can either use a straight line. Your textbook will use a bracket. You put the lower bound on the bottom and the upper bound on the top. Okay, a lot of people like to skip this and say, do I have to write it down? The answer is yes. You're notating that you understand this is a definite integral instead of an indefinite integral. Now, to get our answer, we're going to take the top number. We're going to plug it into the resulting integrated function. So we would have 3 cubed over 3 plus 3. We're going to take that amount and subtract the result of plugging the lower bound into the integrated function, which in this case would be 0 cubed over 3 plus 0. Okay, fraction answers are better answers. Okay, if you are going to give a decimal, you need to make sure you go to 3 decimal places. What's 3 cubed?
27.
Divided by 3?
9.
Plus 3?
12.
Minus what? 0. This is the exact area under the curve of the function x squared plus 1 from 0 to 3. It's the exact area. Okay, so just kind of giving you a visual of what that looked like. Okay, I'll even sketch it on the side. X squared plus 1, hopefully we would all recognize that's a quadratic function shifted up how many? 1. Okay, it's opening up. Okay, and we're talking about the area under the curve from 0 to 3. Okay, what we've just found is the exact area under the curve, or between the function and the x-axis. You have a positive answer because the function is above the x-axis. You're going to have a negative answer if the function is below the x-axis. Okay, no plus c anymore. Okay, when you're evaluating a definite integral, you have a lower and upper limit. Okay, integrate the function, make sure you show your upper and lower limit. You always plug in the upper limit first, and then subtract the result of plugging in the lower limit. Okay, it's that simple. Go ahead.
What did you say about being positive or negative? What is it?
The function's above the x-axis, the answer is positive. If the function were below the x-axis, the answer would be negative. What do you think? It's like exciting stuff. You know what we're going to do next chapter? We're going to actually take that area and we're going to rotate it about the x-axis and we'll get a rotational solid that we'll find the volume of. It's going to be so fun. I even have like props to show you. Okay.
Prop?
I do. I have a box of fun.
Oh gosh.
A box of fun. Have I not shown you the box? I will even give you a preview.
Oh.
All right.
Or pretty.
I might want to switch the camera over to the box of fun.
Am I really gonna do this?
She's not gonna want to miss the box. Well,
I'm not. Kylie, I'm not.
I think she'll be fine.
Yeah. Oh, that was a little box.
there's the box of fun.
Steve would have liked this.
Box of fun. See?
He exploded.
When you take a region and you rotate it about an axis,
Oh god.
it's solid. You can even find the volume of a hula skirt.
Hula skirt.
A hula skirt.
Oh god.
For all those
Oh
hangers.
god.
And we can actually find the volumes of something that has a hole in the middle.
Oh no. Oh.
That one's not a good example. Oh, I just have a whole bunch of fun stuff. Okay, this is your future. Are you excited?
All right.
Okay, so let's go to number 1. We'll get to the box of fun in the next chapter. It's coming. It's coming. This is where integrals are much more fun than derivatives. Okay. So, obviously the big key is you got to integrate correctly. What are you writing, Jay?
The integral whale lives in the plus C
I
according to
just
Marina.
erased the integral with
We were very sad. Look, he's right there.
Yeah, you can see his outline.
We wanted him to live.
Okay, let's take number 1.
I don't want a picture.
Okay, how do you know that this is a definite integral instead of an indefinite integral? Because you see what? Numbers. You see numbers. You see a lower bound and an upper bound, okay? Be very systematic about it. Integrate the function first, no plus c anymore. Okay, what's the integral of negative x? Negative 1/2 x squared. What's the integral of 4?
0. 4x.
Plus 4x, okay? No plus c anymore. We are going to integrate from -2 to +3. Okay, so you plug in the upper bound and then subtract the result of plugging in the lower bound. Be very careful in your computation. You shouldn't make mistakes on the simple part. Anybody get an answer yet? It's not a negative answer. Yep, you should get 35 halves, that's right. Minus and negative is plus and positive.
No, that's
You
right.
should get an answer of 35 halves, okay? we did our integration right, okay, when we plug in the upper bound, okay, we've got 3 squared, which is what? 9, so we've got negative 9/2 plus 12, okay, and from that, we're going to subtract, okay, we're going to subtract the result of plugging in the lower boundaries, okay? The lower boundary is negative 2. What's negative 2 squared? Times negative 1/2 would be negative 2 plus negative 8. Okay. So again, however you're going to operate with your calculator or just adding fractions, okay, over here, what's negative 9/2 plus 12 or negative 9/2 plus 24/2?
15 halves.
Okay, so we have 15/2 minus a negative 10, which is plus a positive 10. Okay, what's 15/2 plus 20/2? 35/2. Exact area under the curve. Okay. And again, visually, okay, we're accumulating area. That's why the definite integral is called the accumulation function. Okay, do we have any kind of a clue what negative x plus 4 would look like in terms of a function? It's a line with a y-intercept of 4 and a slope of negative 1. Okay, so there's a basic idea, and we're looking at the area under the curve from negative 2 all the way out to positive 3. We're accumulating area. In this case, it's above the x-axis. Why? That's why the answer is positive. It's the accumulation function. Tyler?
Why do we learn how to approximate the area?
Because all those methods are on the AP test.
Oh, boo.
That's why. Okay.
Little
We
test.
have you do number 2 on yours. This is just like simple and amazing. We'll get to the calculator work later.
So we put one bracket on like the, the integral?
You mean this?
Yes.
Some textbooks will put everything in brackets, and some books will even just put a line and not use brackets. The key is that you need to have something that indicates the lower definition. Not interchangeable. Let's see, Nan, what did you get to number 2?